My pleasure to introduce Steve Hofmann from the University of Missouri. He's going to tell us about square functions and how they relate to the Dirichlet problem and for divergence forming operators. Thanks.
Thanks, Bernard. Thanks for the invitation. It's a pleasure to be here. It's my first visit to Stony, Brook. So, this is a colloquium, so I'm going to start sort of a very classical level. A lot of material might be familiar to many people. So, the situation is this. We're going to begin with a domain omega, so that's a connected open set in RD. And we're going to consider, first of all, just the Laplacian, which is in RD, of course, this operator. And today we're talking about the Dirichlet problem, which is the problem of finding a solution to this differential equation in the interior, finding a monic function in the interior such that u restricted to the boundary is equal to some specified data f. Okay? And so there are kind of two related issues that I want to discuss today. First of all, typically what one does is consider f to be specified within some class. Typically, f is going to belong to some function space y, some norm space. And typically one seeks estimates for the solution that depends on the norm of f in this space. Okay. And there are two related issues. First, the manner in which the solution assumes its boundary data. Okay, you can have, for example, variational versions of the problem where the connection of the solution to its data is a little bit tenuous. You can have other versions of the problem where you assume the data in a continuous way. We're going to be talking about something sort of in between where u is going to converge to the data in a certain sense. Okay? And the second issue is the matter of the estimates themselves, these estimates for the solution u, which give you continuous dependence in some sense on the data. And these are related, as we're going to see in just a moment, because the manner of convergence to the data is often going to be a thing that is related to these estimates and is obtained from the estimates. Okay? So let me first discuss a prototypical situation, which is that the case that D is n plus 1, omega is just going to be the half space, and my space y is just going to be LP, where P is going to be between 1 and 2. Okay? So in this case, the solution to this problem, in that case, let me just quickly fix some notation. In that case, when my data is taken in LP, from now on I'll refer to that as DP. When the data is specified. So, in this case, the solution can be constructed concretely. It's given by convolution of the data with the Poisson kernel. Okay, this is the classical Poisson kernel for the half space. And here Cn is chosen that the Poisson kernel integrates out to be 1. Uniform in T, and of course it's uniform in T because the scale invariance here. Okay. Okay. So in this prototypical setting, actually more generally than that, but it's easier to focus on this prototypical setting. We're going to consider a couple of fundamental estimates. So the first one, they're both, it turns out, natural, but the first one is more obviously natural. The first one concerns the so-called non-tangential maximal function. And it's defined as follows. N star u of x is by definition the supremum over the colon gamma of x of u of yt. And here the cone, just a standard cone, set of yt in the half space such that x minus y has a length less than t. And there's nothing special about taking the aperture here to be 1. You can work with any fixed aperture. That would be fine. And the estimate, the fundamental estimate, is that the non-tangential max of a solution, when used given this way by convolution of the Poisson kernel, is controlled by some constant general Pn times the LP over the data. Okay? And this is fundamental and natural from the point of view of understanding how the solution converges to its data, because there's a sort of standard technique.
So what's small f? Sup of f, yt, what's small f? A u, is that u? Also u?
It's the dimension of the space.
Absolute value.
Oh, u, sorry. Okay, absolute value. Sorry.
You're good.
Okay. So there's a sort of standard technique in harmonic analysis whereby if you have convergence in a dense class, pointwise convergence in a dense class, plus control of an appropriate maximal operator, that implies almost everywhere convergence. So, for example, that classical situation where many people have seen this is in the proof of Lebesgue's differentiation theorem, where you first establish convergence of the integral averages for f that's continuous with compact support. Use the fact that continuous with compact support is dense in LP, and then the Hardy-Newman maximal theorem gives you the appropriate maximal control, which lets you pass to almost everywhere convergence for data in LP. Okay? And we have the same phenomenon here. In fact, again, for continuous functions with compact support, that's our dense class in LP, it's rather easy to see that as y and t approaches x naught, y and t approaching x0, with yt staying within the cone, then your yt converges to f of x, to the data f of x. That's rather easy to see for unit functions with compact support. And then the fact that you've got control in LP of this non-tangential maximal function lets you pass from this dense class to all f in LP. And the only loss is that this convergence is now going almost everywhere rather than everywhere. Okay? Alright, so because of this issue of controlling the convergence to the data, the non-tangential maximal functions are very natural object to deal with it, and the estimates for it are therefore very natural estimates. But there's a second class of fundamental estimates which is perhaps it's not as immediately obvious why this is natural, but it turns out that it is natural and useful. And those are so-called square function estimates. Okay? So the square function of u is going to be defined as follows. We're going to take the integral over the cone, same cone as before, and again, the aperture is really the material. Take the gradient of the solution, square it, and integrate on the cone with respect to the measure dy dt over t to the n minus 1, and then take the square root of that. Because it's a quadratic expression, that's why it's called a square function. Okay? And the estimate is that, in fact, we have the same estimates for the square function that we have for the non-tangential maximal function. This is with, again, 1 less than 2 less than 2. Okay, we're in the setting of Laplace in the half space. Okay. So, at first glance, this is perhaps a bit of a strange object to work with. It doesn't seem as natural as the non-tangential maximal function. But it turns out that it is natural for a variety of reasons. I'm going to primarily emphasize one particular reason, but let me just mention in passing that there are also Fatu type theorems, which say that, sort of conversely, rather than starting necessarily with some data in LP, suppose we just know that we're given a solution for which this square function is in LP. Okay? Then it turns with P strictly between 1 and infinity. Then one can show that, in fact, U is necessarily the Poisson extension of some F that was in LP from U. Which is the thing that's also true for the non-tangential maximal function, but it turns out that the square function gives that as well. Okay? But there are other reasons why we're going to discuss, or one primary reason we're going to discuss what a square function is a natural object to look at. Okay? So, let me make a couple of comments about this estimate. Okay? So, first, it turns out that from harmonic analysis techniques, one could show, in fact, that the square function of u, and the LP norm of that is actually comparable to the LP norm of the non-tangential maximal function of u, with t between 1 and 2. Okay? And so combining that with the estimate for the non-tangential max gives this. It also says that, well, okay, in fact, from this point of view, this is a natural object because its LP mapping property is the same as for the non-tangential maximal function. Okay? But let me discuss the special case P equals 2 where we can prove this estimate directly. Okay? Let's do this one again. Okay? This is a simple thing to prove, it's just integration by parts. Okay? So the key observation to make is that if u is a harmonic function, so the velocity of u is 0, then the Laplacian, or 1/2 of the Laplacian of u squared, is the same as the square of the length of the gradient. And that's just an easy computation to make. This is 1/2 the divergence of twice the, well, let me write this way. It's the divergence of the gradient of u times u And when the divergence lands here, that's Laplacian, and this is harmonic. And when the divergence lands here, you get this. Okay? So what that says is that if we want to compute the L2 norm of this thing, we're looking at the following object. Okay, and I'm going to use Houdini's theorem. I'm integrating x first. I'm integrating t from 0 to infinity. Grad u of t squared. Then, let me take n of these. Remember the horizontal integrations are in n dimensions. I take n of these, and that makes up to a constant, an average over the n-dimensional ball radius t in the x variable, and then I have dy t times dy dt. Okay? Of course, this is just doing 1. And now I have an integral over my domain of 1/2 the Laplacian of u squared times t dy dt. Now just use Green's theorem. Notice that t is a solution, is itself harmonic. So when the Laplacian lands on t, I get 0. So it's just 0 plus the boundary terms. The boundary terms are going to be up to constants. I'm going to have u times the normal derivative of u times t restricted to the boundary, but that's when t equals 0. And of course that means that goes away. And then there's another term, I guess, with the opposite sign. And then I just have u squared times the normal derivative of this. It's the outer normal. But the normal, since we're in a flat situation, the boundary is flat, the outer unit normal is just a purely vertical variable pointing downwards, vertical vector pointing downwards. And so we take the derivative here. The normal derivative gives you -1, and that just makes the L2 norm. And u, this is u on the boundary, which equals f on the boundary. Okay? Alright. So let me point out that there's really one thing that was required to make that last argument work. Was that t is a harmonic function. Okay? T, of course, is the distance to the boundary. Right? When x in the half space, t is the distance to the boundary. So the thing that made this argument work was that the distance to the boundary was a solution of the operator question. And in fact, let me point out that, okay, this would work for any operator for which, of course, when you integrate by parts of a more general operator that's not necessarily self-adjoint, you would pick up the adjoint of that operator here. So what you really need for a more general operator is that the adjoint of that operator have t, or have the distance to the boundary as a solution. Okay? Come back to that point later. Okay. So now let me talk about the case of more general operators. And for me, more general operators are going to be divergence form, second order divergence form operators. Okay? And we're considering in RD, L is going to be minus div a grad, which means minus sum over I and j from 1 to d, d by dxi, aij, d by dxj, where this matrix aij is going to be bounded and measurable. And uniformly elliptic, which means that there exists some positive lambda such that for all vectors C and Rn, or NRD, lambda times the modulus of C squared is less than or equal to the inner product of the vector A, C, C. Okay. And again, let me restrict, although it turns out it's not much of it's not a big restriction. Let me restrict to the prototypical case again, where our domain is a half space. Okay, so D is going to be n plus 1. All right, and I'm still going to be talking about data in some LP space. All right. Now, in fact, when we allow for bounded measurable coefficients, this is actually working in a half space is not such a big restriction because if you pull back from a Lipschitz graph domain, so omega of the form of xt, such that t is bigger than phi of x, where phi is a Lipschitz function. Then the pullback of an operator of this form from such a Lipschitz domain to the half space is another operator of the same form. Okay. And moreover, you could do this in such a way that if your original operator happens to have t-independent coefficients, then the pullback mechanism preserves the t-independence. I'll come back to that point in a moment. Preserves the class that we're talking about. It also preserves, well, if you choose the right pullback, it preserves t-independence. Okay. All right, so the first comment I want to make about these general operators has to do with this comparability of the square function and the non-tangential maximal function. Still defined the same way. This is a result of Ulmer, Jerison, and Koenig. Sometime in the 80s, I guess. And what they proved is the following. They showed that if, again, let me state it in general, it doesn't specify. Okay, I'll state it in this situation. Is that if the Lebesgue measure on the boundary dx is A infinity equivalent to harmonic measure with some fixed pole. And actually, I'm being a little imprecise as we do this on various scales, and within the scale, you'll insist that it's A infinity equivalent to uniform constants. Let's not worry too much about what this means. This A infinity property, just think of that as scale invariant absolute continuity. So it's absolute continuity with scale invariant quantitative estimates. Neutral absolute continuity. Okay. It turns out also that this property, this scale invariant absolute continuity of the harmonic measure with respect to the surface measure, is equivalent to having solvability of the Dirichlet problem with LP data, in this sense of having, say, non-tangential estimates for the solution. For some p, strictly between 1 and 2. Okay? So get this scale invariant absolute continuity if and only if there's some p for which the Dirichlet problem with LP data is solvable. In the sense of the topic. All right. Now,
You can raise the word this here.
Yeah. I should have raised the word. Okay. All right. So then, it turns out that these two equivalent things, either of them implies that one has this, the comparability of the square function and the non-tangential maximal function. Not just for this particular p, but for all p. Okay? So let me briefly explain why that's true. It turns out that this infinity property, when omega and dx and omegas are usually absolutely continuous in this scale invariant way, it says that the green function with a fixed pole is comparable to the distance to the boundary a lot of the time. Whatever that means. Okay, why is that good? Well, if you think about how this integration by parts argument went, it means that at least at local scales, when you're avoiding the pole, then G in this variable is an adjoint solution for the operator L. Okay? It's an adjoint solution, which means that if you could substitute this for the distance to the boundary, then you can carry out this integration by parts argument, and it still works. Okay? And that's the fundamental idea. Okay, well, so that's nice, but notice that, of course, it requires that you know the same infinity property, which amounts to knowing that you have at least some solvability results. Okay? On the other hand, it turns out that there's a converse. This is basically due to Pinning, quote, pi for Toro. Although it's based on earlier ideas of Garnett's and of Goldberg. And what they show is that conversely, if there exists some p naught, say, such that S of u square function and the non-tangential mass are comparable in LP naught worth. It requires a little more than that. It requires this in some local scale invariant way. Okay? You need to be able to localize this estimate in a scale invariant way. But if you have the appropriate local scale invariant comparability of these two objects, then that actually implies that omega and Lebesgue measure are infinity equivalent. Okay? And therefore, you got that there's at least some other P, not necessarily the same one, for which the Dirichlet problem is solvable with data LP. Okay? So P1. Okay? So that gives us potentially a tool for establishing solvability results. Is if you can show that you can establish the comparability between the square function and the non-tangential max, then you could deduce solvability from that. And in fact, this is actually done by, again, in the same paper, canonical equatorial, in 2 dimensions. That is, if we're in the setting of the half space, n plus 1 equals p. Okay? All right. And so the key idea there is as follows. That, okay, in this case, our coefficient matrix A is 2 by 2. And let's write it, let's say, specifically this way. What you notice is that if this entry, this scalar entry C is 0, then the transpose matrix is of this form. And notice that then the corresponding adjoint operator equals T. Okay? So T is a solution of the adjoint operator, which says that if you have this triangular matrix, then you could carry out this integration by parts argument to establish one direction that the square function is controlled by the non-tangential max. It turns out that similar considerations let you go the other way. Turns out then you can localize it and you can invoke this theorem here and you get the solvability of the Dirichlet problem for some P. Alright? Of course, the problem is that in general, this constant is not 0. On the other hand, what is true is that since if n plus 1 equals 2, then C is a scalar, and it's a bounded thing, it's in infinity. So C can be viewed as the derivative of a Lipschitz function. Okay, and so it turns out then that working with this matrix in the half space is equivalent to working with a triangular matrix in a Lipschitz graph domain. I guess where the domain is given by the graph of negative phi. Okay, the boundary is given by the graph of negative phi. Okay, well that doesn't really happen by itself. But what then you do is to observe that, okay, instead take this triangular matrix, work in the half space. Okay, then you can carry out the integration of parts arguments. And then you realize you can still do the same thing if the Lipschitz norm, if you work in the Lipschitz graph domain where the Lipschitz norm is very small. And then you can do a bootstrapping argument to get back to this Lipschitz domain where your problem is equivalent to your original problem. Okay. Alright, but what about the higher dimensional situation? tell you, I overlooked one thing. This is all working. Okay. This is not the only thing you need. Okay. It's not just. Okay. Well. Okay. It's in addition to the triangularization. Okay. In order to carry out this integration by parts, you get that L star of t is 0, not just when you have a triangular form, but it also requires t independence of the coefficients. Okay. So the coefficients are t independent and triangular, then you have this. So let me, before I talk about the higher dimensional case, let me briefly make a comment about t independence or not. Okay? So basically the theory splits a natural way into two parts. First, when the coefficients, so we're in half space there. When the coefficients depend on x only. And then, second theory, when you have some regularity omega of xt in the t variable. To be a little more precise, you're controlling the modulus of continuity of A of xt at the boundary. Okay? So there's actually a well-developed theory in this case due to Robert Pfefferman and Amy Piper. Which says that if you know that this t-independent operator is good, okay, meaning that the Dirichlet problem is solvable for some t, and if you have a certain appropriate amount of regularity in the t variable, roughly speaking, it's a square-Gini condition of the modulus of continuity, but in a scale-invariant way, then you can deduce solvability for the LP Dirichlet problem for perhaps some other p. Okay? And this is somehow best possible. There are counterexamples that say that that's sharp. You can't. To get some DP type solvability, you have to have something like a square-Gini condition in the t variable. Okay? So the theory splits naturally into two parts. We know basically what kind of regularity you need, given that you can control the t-independent guy. And therefore, it's of interest to understand what happens in the t-independent case, because that serves then as a base of operators that you can perturb in this way. Okay? Alright, so we'll work with the t-independent case, and in that case, for a triangular matrix, L star of t vanishes. Alright, now, what about the higher dimensional case? Okay? Well, again, let's split we now have an n plus 1 by n plus 1 matrix. And let me sort of split it schematically in the following way, where here A is an n by n block, D is a scalar, and B is an n-dimensional column vector, and C is an n-dimensional row vector. Okay? Alright, well, the same thing would work, the same kind of integration by parts argument would work to control the square function. Again, if this vector C is 0. So if we have sort of a block triangular form. Okay, because then for the adjoint, that would mean this guy is 0, and it's in addition t independent, then then the distance to the boundary is an analytic solution. Okay? The problem now is that some arbitrary elliptic vector is not necessarily the gradient of a Lipschitz function. Okay? So we can't do what you did in the case when n plus 1 was 2. On the other hand, you don't really need, in fact, you don't really need C to be 0. It would be okay if the divergence of the x variable, let's see where the variance is, which suggests trying to do some kind of Hodge decomposition. Alright? Well, okay, the problem is that the Hodge decomposition that you need should be one for an n-dimensional operator that's adapted to this n by n submatrix here. Okay? And those, you can't do that kind of Hodge at the level of infinity. Okay? Only for a very narrow theorem p equals 2. Okay? But nonetheless, it turns out that this can be made to work, and in these last few minutes, let me describe briefly how this can work. So what we're going to do is, okay, first of all, you have to localize the problem. Okay, so you're working in some given cube, which is a cube contained in Rn, and our domain is the half space, and associated to Q, we're going to work with a Carlson box, RQ, which is the n plus 1 dimensional cube that you get by extending Q up into the half space with height, the side of the cube. Okay? And then if you localize, then you cut off by the indicator function of, let's say, dilate 5 times the cube. Since C was an L infinity, this is now any LP space that you like. In particular, it's an L2 plus epsilon. And we can make a Hodge decomposition since this is now an L2 plus epsilon, we can make a Hodge decomposition where this becomes, it turns out that what we want to do is take the transpose of this matrix, this n by n submatrix here, and what we said, so we're making a Hodge with respect to what I'll call L parallel stuff. L parallel is the horizontal part of L. So this is the x variable of that parallel part for its transpose. Okay? Alright, so we can get a Hodge decomposition where this splits into this thing plus some other vector h, where the divergence of h is 0, and where both h and the gradient of phi belong to L2 plus epsilon, with norms, of course, controlled by the norm of this guy. Okay, and then we're going to make a change of variable. We're going to map our domain into itself in a one-to-one onto fashion using the following mapping. Xt is going to go to t plus, and I'll explain what this thing is in a moment. where P epsilon t, sorry. This epsilon is not the same as this epsilon. Okay. This is just some epsilon chosen suitably small to make the mapping be 1 to 1 or 1 to 2. Okay. So P epsilon t is going to be the heat semigroup with elliptic homogeneity at the scale epsilon t for this operator L parallel star. Okay? Alright. And so what happens then is that my matrix gets transformed under this mapping into something where down here I've got H plus A parallel star of radiance of P epsilon T of P. Which is an odd looking thing. Okay?
How is your mapping and mapping? I don't quite see it. It's x comma t goes to something and r.
Oh, it's not equal. I'm sorry. Sorry.
But this is t.
And this is at. I'm sorry. And this is at x. Okay. I'm sorry. Okay. So notice. So this is an approximate identity. And as t goes to 0, this goes to 0. So as t goes to 0, it's mapping the boundary into the boundary. All right. Okay. And inside, okay, I mean the philosophy is that this thing is an approximate identity. If we're truly the identity, this would. I'm sorry. I'm ripping this back. So what I'm mapping into. Yeah, sorry about that. What I'm mapping into is this. Xt goes to x, and then t is being replaced by this place. Okay. Alright. So, yeah, as right. So you think of this when this approximate identity were truly the identity, then this wouldn't be this, it would just be the identity mapping. So this is just distorting things a little bit. But in a way that you see, the thing that this does is the following. I originally had, I wrote a parallel here, but what I really mean is this, the length stuff. Okay? You see, originally I had, at least locally, C was equal to this divergence form thing, plus little a star times the gradient of phi. And what this is letting me do is, by making this change of variable, it's letting me replace this part by the same thing, but with this P injected in there. Okay? Now, why is that good? Well, okay. So now you consider the transpose of this matrix. And this row vector down here becomes a column vector here. And then I consider the operator L, let me call it L tilde now, it's the transformed guy. Okay? It's the operator corresponding to the transformed guy. And I apply it to T. And what I would like is that it would be 0. Okay? Unfortunately, it's not 0 anymore. It's not 0 anymore. Because there's this garbage here. The T and this divergence free thing is fine. That doesn't really hurt me. Okay? But now, what happens is that I don't get 0, but I get stuff that involves taking derivatives of this object. Okay? And so I get terms when I integrate by parts involving derivatives of this object. And why is this object better? So what can I do with that object? It turns out that there are various terms, okay. Within, so So when we carry out this integration by parts as before, you're going to have u, you're going to have L tilde star of t. Let me not write that. Let me write this. You're going to have u squared, you're going to have L tilde star of t. And then you're going to have, wow, dx dt. Okay? And, okay, to make this all legal, I can't actually work in my original domain anymore. That has to do with the fact that this phi is actually not a Lipschitz thing. It's only in W1, 2 plus epsilon. So that adds some complication, but let's ignore that. And so what I end up getting is sort of paraproduct-like terms. Let's not worry too much about what that means, but basically what that means is there are terms for which you can in other words, these are terms of roughly of the form. You're going to have three things working for you. You're going to have some, let's say, f of xt, and another h of xt, and another thing, maybe k of xt, dx dt, over t. This is just a normalization. Okay? Where this thing, well, where say this thing gives rise to square function estimates. This thing gives rise to non-tangential estimates. And where k squared dx dt over t is a Carlson measure. Which means that if I call this du, then du of the Carlson box is uniformly controlled by the Lebesgue measure of Q. And I think I drew a picture of a Carlson box earlier. Yes, over there. Okay? So it may be a little mysterious where these come from, but here's the punchline and then I'll stop. The reason this gives rise to terms of this form, okay, so first of all, these terms are good because, well, it's basically an embedding level of Carlson, which lets these terms be good. Control. Why do we get terms like that? It's because square functions built out of derivatives of this object. Okay? If I look at this kind of square function, where I have, say, the gradients and maybe a t derivative of this thing p epsilon t of phi, y squared 1p over t to the n minus 1. These square functions turn out to be bounded. Okay? On, well, a range of LPs, but for us it matters that they be bounded in L2 plus epsilon norm by the W12 norm, or W12 epsilon norm. W1. The L2 plus epsilon norm of the gradient of phi. And why is that? This is a consequence, actually, it's an equivalent thing to the solvability of what became known as the Dirichlet problem, which has to do with finding the square root or to controlling the square root of this operator that I called L parallel. That. square root of this thing in L2 and L2 plus epsilon. Let me call it P. 2 and 2 plus epsilon. So the square root of this guy is controlled by the L2 normative gradient phi.
So the operator is not self-adjoint, so what does the square root mean?
Okay, so it's defined in terms of functional calculus, and it turns out that ellipticity gives enough acretivity that allows you to define square roots. Okay? That's not functional calculus. I can say more if you want, but I guess I should wrap up now. But the point is that it turns out that this kind of estimate, which was proved a few years back, turns out to be equivalent to saying that you have these kinds of square function bounds for this object, and it turns out that these are the kind of objects that arise when you perform this integration by parts arguments after making this change of variable to transform the matrix A into this other matrix. So that's a good place to stop. Thanks for the invitation once again.
Can one get any decent theory in this context if you don't assume uniform ellipticity?
That's a good question. Some sort of degenerate elliptic. Okay, that's a good.
A is going to 0 at the boundaries.
That's a good question. What I guess, okay, at the moment, I think this is kind of a wide open question. But what I guess would happen is that if you control the degeneracy by some kind of A infinity weight, then maybe one could do something. And elliptic operators with A infinity weight controlling the degeneracy do arise in a natural way. If you pull back under the action of a quasi-conformal mapping, that's the kind of degeneracy that we'll get. So I wouldn't be surprised if such a thing were true, but at the moment that's I think pretty open question.
Well, I mean, a typical geometrical example would be if you look at a conformal model for hyperbolic space and you just look at the Laplacian on it, then that is not uniformly elliptic as you approach the boundary.
Right.
And then many other similar geometric problems. So.
Right. No, that's a very interesting question, but at the moment, to my knowledge, it's a pretty much an open question to deal with these kind of problems in that situation.
I'm not sure I completely understood what the punchline here is. So you're giving a version here of the fundamental estimate? Is this?
Yeah, right. So, right. Yeah, I don't blame you for not following it because I was waving my hands like crazy at this point. But yeah, so it turns out that when you carry out the integration by parts argument as before, to try to get control of the square function, say in L2, what you need to worry about is what happens when the adjoint operator hits the distance to the boundary. And ideally, you would like this to be, you would like the distance to the boundary to be a solution, in which case it just goes away. Okay, that doesn't happen because of the presence of this term. But it turns out that this term with this this particular adapted approximate identity in there is much better, is much more amenable to being handled than the one where that approximate identity is not there. Because then what happens is that you actually carry out this computation and then you integrate by parts some more, and you end up with these pair product things, which are controllable. And the reason that they're controllable in the end is because the square function, this kind of square function built from these guys, turns out to be controllable by the W1 2 plus epsilon norm of phi. And the reason for that is because it turns out that that kind of control is equivalent to this estimate for the square root of the parallel part of L, or of L star, which was a problem that was solved about 10 years ago.
So if A, if coefficients in A were C2, you'd have a running motion model for this. Is there any understanding of any of this business, like from a probabilistic point of view?
Okay, the short answer is with this kind of minimal smoothness, the short answer is I don't know. Any questions? I don't know.
Other questions? Thanks, speaker again.